Science on Surfaces. A bigger perspective on the small.
Welcome to this podcast, Science on Surfaces, a bigger perspective on the small. Here we zoom in on science that impacts our everyday lives. And today we will talk about energy storage and the relevance of surface science for some energy storage methods. My name is Malin Edvardsson, and here with me in the studio I have Professor Bengt Kasemo. You are Professor of Physics at Chalmers University of Technology. Welcome.
Thank you.
So you have long experience in surface science and you've worked a lot with sustainable energy, the energy systems of the future and energy storage. And with the overall global ambition to shift from fossil to renewable energy sources, so for example wind and solar, the need for energy storage is particularly important. But of course it's important for many other aspects as well. So could you say something or comment on the overall benefits of and need for energy storage? What are the benefits and drivers for this?
Generally, energy storage enters because the time point when you produce energy and have optimal opportunities to produce energy doesn't always coincide with when you need energy, and therefore you need some kind of intermediate storage. So the energy system generally is built up of production of the energy, maybe transport, storage, use at the end. And to store energy there is important for several reasons. One is if we have intermittent energy sources like solar or wind. It blows sometimes, sun shines sometimes, but not always. And therefore we want to store energy from these sources for later use, for example, for the night. Mm-hmm. But the storage also has another function. If you can store energy, you don't need as much maximum power to produce energy for peak energy use. If you can store energy and buffer what is produced exactly at that time, if you can buffer that with using also some stored energy, you have a much better situation and you can reduce actually the total power that is built. Energy storage is important on essentially all time scale. When we fill our gas tank on the car, we fill it for the travel for the maybe next few hours or for the next day. When we store energy from summer to winter, it's on several months. And when we store energy for long term, for tens of years, decades, we have many years as a relevant time scale. And it's interesting to think about our fossil energy resources as stored energy, because it is stored energy that nature stored for us hundreds of millions of years ago. And we harvest that for use on the day scale, on the month scale, on the maybe decades, at most a few centuries. But still, it's a storage of energy that makes our energy supply possible.
You also mentioned the perspective, so time scales, but also static versus mobile. I'm thinking you mentioned for the cars and stuff. So that is also an aspect in terms of energy storage or usage, perhaps.
Yes, that's right. So permanent storage on stationary systems is of course easier. We could take a water dam that can store energy. The water dams of a country like Sweden can store energy for months of use. They are not mobile, but they are big. While the car tank or the battery in an electrical vehicle have to be mobile. And there you need to consider volume, weight, and so on. And also that in these cases the time scale is usually much shorter than years, months.
So you've mentioned a few ways or methods to store energy: water dams, oil. What other methods do we have?
Well, we could say that we can store energy of different qualities. We can store energy as electrical energy in batteries. We can store energy as chemical energy in fuels. And we can store energy as heat. Basically, you could say that the quality of the energy is falling as you go from electricity to chemical energy to heat. Especially if the heat is low temperature, it's usually called low quality.
And what do you mean by quality?
Yes, the quality is what it can be used for. So if you have something that is 100 degrees or 200 degrees hot, you can use it to heat a house, but you can't use that without elaborate systems to produce electricity. While electricity can easily be used to drive electrical engines, but it can also be used for heating.
Okay.
It can be used for anything you want. Another aspect is, of course, that to use electrical energy for heating is in a way waste of quality. It's better to use some other lower quality energy for heating.
Okay. So where is the relevance of surfaces here?
The relevance of surfaces is that many of those storage systems, especially the chemical storage systems, which are in a way chemical and electrical combined, they use surfaces. And the best examples, I can mention four examples. It's a battery, it's a fuel cell, it's a supercapacitor, and it's a catalytic process. So for example, in a battery, both in a battery and in a fuel cell, you store energy as chemical energy in the electrodes when you have charged the battery. So then when you use the battery, you allow chemical reactions to happen at the anode and the cathode, which creates currents in the loop between the anode and the electrode and the electrolyte. So in the battery you have chemical energy and you have electrical energy. The difference between a battery and the fuel cell is that all the energy that is stored in a charged battery is in the electrodes. So you always carry that fuel, if you want, with you. In a fuel cell, you also have reactions at the electrodes that produce a current, but the reactant, the energy, chemical energy, comes in from an external source, very often hydrogen, but you can also use other fuels. And when the hydrogen reacts in several reactions on the anode and cathode to form water, you release energy in the form of electrons that go in the external circuit and create a current.
Okay.
So the difference between a battery and a fuel cell is essentially that the fuel is separated from the battery, from the fuel cell.
And so where do we use fuel cells?
Fuel cells can, for example, be used, it's not a storage system actually, as a battery is. It's the storage system is there in the fuel, in the hydrogen. However, very often you think about the fuel cell as something that produces electricity for you with stored energy. So it's the hydrogen that is the storage medium, or methanol in some sense. So the hydrogen is the stored energy, but you need the fuel cells to produce electricity. And you could, for example, produce a hydrogen with electricity. Then you have a loop. Electricity, when you have a surplus, produces hydrogen. Hydrogen in the fuel cell produces electricity back when you need it. But it could also be hydrogen that is created by solar energy, by photochemical processes, or by electricity from a solar cell.
Okay.
So that's where the fuel cell enters into the storage system as a means of producing electricity from stored energy, chemical energy.
And in what situation would you use a fuel cell?
For example, let's go to a place which is far away from the grid, from the electrical grid, and you produce hydrogen during the day by some photochemical means or by electrolysis with electricity from a solar cell, and you produce that hydrogen during the day. When the night comes, you have no electricity because you don't have the grid. But then you can use the stored hydrogen to produce electricity from a fuel cell. So in this example, the stored hydrogen and the fuel cell is an alternative to a battery. To get night electricity.
And what about the supercondenser?
The supercapacitor.
Supercapacitor?
The supercapacitor is a way of, as in a normal capacitor, of separating charges in double layers. But you place the geometry such that you have very, very small distances and you get extremely high charge densities. We're talking about 10 to 100 times more energy than in a normal capacitor, or even 1,000 times compared to a battery. The advantage is that they are extremely fast. This means that you can get very high power during a shorter time. So a supercapacitor today it could be seen as a complement, as a competitor to a battery, but I think it's better to see it as a complement to a battery, where you can, depending on what the need looks like, if you need fast energy, high power, supercapacitor. If you have more lower power, a battery.
And what is then a high or low power?
Well,
range?
You can say to run the car at leisure, at normal speed, it's normal, and high is very fast acceleration.
But we're talking about moving a car. So
for example, but it could also be in some chemical processes where you need high peak powers, and when you need high peak powers during a short time.
And you mentioned the fourth one was catalysis?
Catalysis, yes. Catalysis, and I can take catalysis and photocatalysis under the same heading. And how surfaces enter there. We could go back to the traditional catalysis of oil refining. So oil refining from crude oil produces products which go all the way from hydrogen, which is not really wanted because there's too much, to light hydrocarbons like methane, which you also don't want because it's better to use natural gas and so on. So, but you have these fractions of heavier and heavier molecules down to gasoline and to diesel and so on. And this refinement in refineries of crude oil to these products was originally done by thermocracking. You let the oil pass towers with different temperatures and you got different products. But when so-called catalytic cracking or cat cracking was introduced, you got much better yield of the molecules you wanted. And these catalysts were called zeolites. So the zeolites have a pore structure that can break very long hydrocarbon molecules, complex hydrocarbon molecules, into smaller pieces. And when they do that, you produce higher yields of the gasoline and diesel, for example, or whatever you want.
So this is like a mineral?
It's like a mineral, a very porous mineral,
structure,
and it's porous on the nanometer scale or even sub-nanometer scale. So that's one of the role models for catalytic cracking. But catalysis is also used, so that's for breaking apart molecules, but more generally catalysis is used to produce chemicals by entering reactants on the surface of a catalyst, and then you produce some product that you want. When we talked earlier about fuel cells, the reaction that was promoted there actually also uses a catalyst in the fuel cell of platinum. And what the platinum does is that it combines hydrogen and oxygen to water, which is a lower energy state, and the difference comes out mainly as electricity. But there are many reactions where you want, catalytic reactions where you want to go the other way. You want to crack water, split water, back to the energy-rich hydrogen and oxygen. And again, you can use electricity or electrical potential to help that process, but you can also do it purely thermally. So you have the catalyst, you have water, and you provide some heat, and the catalyst cracks water to hydrogen, and you have your fuel. So in some processes, you take help from light, for example, solar light, to make a photocatalytic process that helps splitting water back to hydrogen. And then you store the hydrogen and use it when you need electricity again, for example, in a fuel cell. And more generally, catalysis can be used for many different reactions in the energy system. And it's, of course, all these examples that I mentioned, batteries, fuel cells, capacitors, and catalysis are basic surface phenomena.
So you mentioned that surfaces are involved in all these four methods.
The examples, yes. And I could add, actually, hydrogen storage. There are several options for hydrogen storage, but one is in a tank, a gas tank, and pressurized. But you can also store hydrogen by letting hydrogen react with certain metals to form so-called metal hydrides. A typical example is magnesium. So you let the hydrogen react with magnesium and form a magnesium hydride, and it stores hydrogen at a density which is higher than you can achieve by gas storage. It's almost like a solid hydrogen. And then you need some energy to release the hydrogen again, but if you're willing to pay that price, you have a very, very convenient storage system.
So all of these are in use already?
They are in use already, yes.
So what would be a typical situation for each of these where they are applied? Or are they all used in similar situations, or...?
No, they are used, I would say, in different systems. For example, a fuel cell can be used in a house if you want to produce electricity because you have produced in some way hydrogen.
Or if you're off the grid, as you mentioned.
Right. In the batteries, it's the same. But when you mention battery, you think mainly of cars, but you can also have stationary batteries. So they are similar situations, but for example, the catalysis is, I at least think about more large-scale production of hydrogen by photocatalysis or by electrocatalysis and so on. So then it's more bulky process that is large industrial scale, and catalysis is a very big process generally in chemical industry. So there exists the infrastructure and the knowledge to take this general process into the energy system to produce fuels.
And the supercapacitor, we talked about that.
Supercapacity is actually, to be honest, more on the development stage.
Okay.
So it's not, I wouldn't say that it's used regularly. It's very, in that sense, very different from battery fuel cells and catalysis. It's more on in the future.
And then it could be replacing batteries.
Right. Replacing or complementing.
Replacing or complementing. So, what surfaces or surface materials are used in these?
Several of the examples I had, batteries, fuel cells, are electrode materials. And what you want to do is to have, for example, materials that do the battery function or the fuel cell function, but at the same time, since they are in mobile system, that they are low weight
Of course.
and also low volume. So you want to have high power density. But at the same time, they are expected to perform the battery function itself. So there may be some conflict between the need for weight volume versus efficiency.
Right.
And this is, for example, I think the most well-known example is a switch from lead battery to lithium battery. And in between the nickel, cadmium, and so on. So the switch of material there was very much motivated, of course, by the weight. Lead is very heavy and also bulky volume-wise. So the switch there is motivated by weight and volume, especially weight. And then you run, of course, into the problem of the harvesting of lithium as a material, which may be restricted, and therefore a lot of battery research is devoted to finding new materials with similar advantageous properties as lithium, but more available, more accessible, like sodium. So, for example, I think you could call it almost, in the conceptual world, a sodium battery instead of a lithium battery would be a great breakthrough without losing performance.
And is that on the way, or is
it's on the way by research, and there are other materials, other ions that you can use than lithium, sodium, and so on.
Okay.
So there's a lot of research to circumvent the material problem by going to new materials that are more abundant.
So these surfaces, how important are the properties and the surface condition?
They are very important. Of course, the surfaces should be durable. They shouldn't be consumed or degraded. In catalysis, for example, one of the standard enemies in catalysis is what is called poisons. So, and the reason that in a fuel cell or in many catalytic systems one uses platinum or platinum metals is that it resists poisons.
And what do you mean by
a poison is some chemical that places itself or is absorbed on the surface and binds stronger to the surface than what you want to perform a catalytic action on.
Okay.
So
it
for
blocks
example,
the access.
It blocks the access. So sulfur can prevent hydrogen and oxygen from entering the surface and react. And this was, for example, in the development of catalytic converters in cars, which are based on noble metals like platinum, rhodium, palladium. This problem led to the prohibition of sulfur-containing fuels.
Oh, okay.
So sulfur was not only an environmental crook, it was also a poison that could poison the catalyst.
Mm-hmm.
And make it so by removing more and more the sulfur from the catalyst, you got a longer life of the catalyst.
Okay.
And in this case, the reactions were not to produce water from hydrogen. It was to convert carbon monoxide to carbon dioxide.
Mm-hmm.
And it was also convert nitric oxides, NO and NO2, to reduce them to N2.
Mm-hmm.
And both these reactions occur simultaneously on the catalytic converter in a car, in a gasoline car. But the action for that requires that the exhausts don't contain any poison like sulfur that poisons and destroys the catalyst. So it's a very and that system, that concept, can be translated into any new catalytic process that you employ for example, producing biofuels and producing hydrogen from water which may not be clean enough, and so on. You always need to keep an eye on poisoning components in your feedstock.
So contamination could be a problem. What about wear in a battery, for example? Would the electrodes wear out?
They can also wear out, because what you do in a battery is that you repeatedly, cyclically, you convert the electrode to a new chemical compound. You oxidize it, you reduce it, back and forth and back and forth. And such reactions always cause some kind of microstructural changes. And these microstructural changes can eventually ruin the battery. So this means that in the design of the electrodes, you may need to put in some stabilizers that are purely for the sake of preventing the degradation of the battery.
So if you think about the lifespan of these methods, sort of like how long you can use them for, do they have a limited lifespan? Or
I think they all have a limited lifespan, but I think looking back into the history of developing catalytic processes, what you learn for a particular process, if it's sufficiently desired, if it wanted enough, what you learn is to make the catalyst better, to make it more stable, to make it resistant to poisons, to make it resistant to structural changes. And if you don't manage on that side, on the electrodes or the catalyst, you also treat the feedstock. You say, what is it that destroys my catalyst? And you remove components of the feedstock, and eventually you build a system with sufficiently longer and longer life. I think for the first catalytic converters in cars were questionable if they could run more than 50,000 kilometers or something like that. And today I think the number is 20, 25, 30,000 kilometers.
So certainly improving.
So it's a stepwise, successive improving of the whole process.
So are there any other challenges or limitations in terms of these surface-related energy storage methods?
I think the limitations in the end is the economy of. I think you can make a catalytic system that does what you want it to do, but it may not be affordable. So it's a competition between many different systems where the economy puts a roof, a ceiling, for what you can allow 1 liter of gasoline to cost. So you could make it if you could afford a high price for it, but if it's not affordable, it will not be a technology.
Right, of course. So then you're thinking about costs for materials that are included, for example, or manufacturing, or
all the costs. For example, purifying the feedstock. If that costs too much, the end price will be become too high, or
Yeah.
if the catalyst needs to contain too much noble metals like platinum, it may be too costly.
So what about the energy extraction from these different storage methods? Will you get the same amount of energy out as you entered into the
Never.
system?
Never.
So to say. Never.
No,
Okay.
you will always lose something. For example, I mentioned the example of hydrogen storage in a metal hydride.
Mm-hmm.
Since what you basically do when you form magnesium hydride from magnesium and hydrogen gas, you form a chemical compound. And it's an exothermic reaction, so you get some heat. And usually that heat is waste heat.
Yes, of course.
Then you need to supply heat to release hydrogen again. And the overall efficiency depends on how much you lose on these two, the heat that you need to vent away and the heat that you need to supply to get access to the hydrogen. But to take another example, for example, in a fuel cell, if you take hydrogen as fuel, and you can, for example, run a diesel engine very well on hydrogen as a fuel. But the overall efficiency of the combustion engine is at most 30%. I would say 20 to 30%.
Okay.
But for the fuel cell system, it's something like 70%, even if you accept losing the thermal energy. So there is a big advantage in this number, but you never get 100% back.
But just as an example, if you take these small batteries that you would use in a torch or something.
Yes.
If you use those rechargeable batteries and you charge it, then what would the loss be?
I honestly don't know what the efficiency there is.
But it's
I would say that all energy systems have quite large losses. But so for example, the fuel cell example is good, and if we take nuclear energy, nuclear energy used for electricity production, the main part of the energy that is produced is going away as thermal energy.
Oh, okay.
You need to use so much water, usually seawater, to cool away. So there's much more thermal energy produced than electrical energy in terms of watts.
Okay. There are a few challenges. So where do we currently see the most ongoing research to push this area forward?
I think generally the focus today is very much on batteries for electrical storage. Especially if you talk about renewables, renewable energy system. So the battery challenge, batteries with higher power density, longer life, and so on, is probably the main focus. But I think also the chemical systems, if I say so. So to form chemicals by renewable methods, like by solar energy or solar energy photocatalysis, or by pure thermal energy coming from the sun. You can build photoreactors that are heated by the solar energy. So there's nothing electrical there, but you get high temperature. And to use that to produce biofuels into the sustainable renewable energy system is one very important direction. It's a little behind batteries, but I think it will come. We didn't really talk about thermal energy.
No.
We talked about thermal energy as something low-grade energy, but still, the higher the temperature, the better, and you can do more and more things. So, for example, in in a biofuel reactor where you produce biofuel, if you can use energy from the sun to heat the reactor, you have a sustainable energy system to produce biofuels where even the input energy comes from renewables, like the sun.
Yeah.
And I think that's an area where there is a lot of research in that area, but it's not on the production level yet.
Yeah.
Then we have some futuristic energy storage systems like the geothermal energy.
Mm-hmm.
Geothermal should not be mixed with what we call energy when we drill 100 meters or so. We're talking about drilling 10,000 meters or more.
Oh, okay.
Talking about kilometers.
Mm-hmm.
And down there we have temperatures that can rise to many 100 degrees, sufficiently much to vaporize water, to steam, and to use that steam to drive, for example, a turbine. That's one example of already stored thermal energy.
Yeah.
But you can also use similar concepts, but more closer to the surface for solar energy. Solar energy, if you're not very familiar with solar energy, you usually think about solar cells that produce electricity, and electricity that charges a battery or produces hydrogen.
Exactly.
But you can also use heat to store energy from day to night. And so if you have big parabolic mirrors that heat water to several hundred degrees C during the day, you can use this hot steam to melt salts, which has a high energy of melting. So when it goes from the solid phase to the molten phase, you store actually a lot of energy.
Okay.
That you can regain during the night by letting this liquid salt solidify.
Sophisticated method.
It's sophisticated, but then by that method you can then produce steam during the night, and the steam runs a steam turbine in the same way as it does during the day. During the day, the steam is produced directly by the solar radiation. During the night, you have stored energy in these molten salts, and the molten salts produce a steam for you, but you don't need to switch off the steam turbine.
No.
So that's an interesting storage of thermal energy.
So
and these are such solar energy parks are existing in reality at several places.
Oh, okay. So you mentioned there's a lot of focus on batteries. Why is that? Is this a particularly attractive storage?
I think it is.
Method, or?
I think it is driven very much. We get to something that we surprisingly haven't talked about: the climate issue.
Yeah.
So the climate issue is there are many different sources for CO2, but I think one could say that the two major climate crooks are the transport system, the cars, the airplanes and so on, and it's the electricity production by using coal or natural gas. So that's the bulk of CO2. And since one of them is a transport system, you immediately think of switching from gasoline or fuel cars to electrical cars. And I think that's one reason why so much focus is on the batteries, that we need to meet the demands from the climate challenge. You need another source for driving a car than the gasoline, than the fossil. And the obvious answer is today the battery.
So then in this sense, the energy storage method is a limiting factor.
It's a limiting factor
to move in
because
that
you want
direction.
to store energy. So there are two limiting factors. One is the primary energy source, of course, solar or wind or so on. But the second is also the storage, because you can spread out the collection of primary energy over a much larger time scale if you have good batteries.
Mm. Okay. I think that's what we had.
That's what we had
for today's episode.
There is a lot to say about the energy system, but I think if I should say a final word, it is the connection to the climate system is very strong. So when you start to look into the climate challenge, you always end up in one step. You end up in the energy system and say the energy system is a major source of CO2 or greenhouse gases. There are other sources like food and so on, but it's really the energy system that is the primary target for solving the climate, solving inverted commas, solving the climate challenge.
And energy storage is a very big
storage is part of that.
Yeah. Okay, so that was interesting to learn more about the relevance of surface science in relation to the energy storage. So that's what we had for today. So thank you for listening to this episode of Science on Surfaces, a bigger perspective on the small, with me, Malin Edvardsson, and Bengt Kasemo, Professor of Physics at Chalmers University of Technology. Thank you.
Thank you.